I'm William Brangham, and this is Horizons. We all know exercise is good for us, but how exactly does it impact the human body? Does it change us at the molecular level? And if so, how can we best harness its power? Coming up next.
Support for Horizons has been provided by Steve and Marilyn Kerman and the Gordon and Betty Moore Foundation. Additional support is provided by Friends of the NewsHour. This program was made possible by contributions to your PBS station from viewers like you. Thank you. From the David M. Rubenstein studio at WETA in Washington, here is William Brangham.
Welcome to Horizons from PBS News. This will come as a surprise to no one, but exercise is really good for us. It's good for you, it's good for me, it's good for everyone. Shocking, right? But why it works and how it works, those things are far less understood. So we're going to spend this episode talking with a man who, along with a big team of others, is trying to understand the profound impact that exercise can have. He is part of a massive, decade-long, multi-site investigation to tease out how, at the very molecular level, exercise changes our bodies and why. In describing this team's first series of papers, published in Nature 2 years ago, our guest wrote this about exercise. Quote, "Its benefits in prevention outstrip any known drugs. 50% reduction in the risk of cardiovascular disease, 50% reduction in the risk of many cancers, positive effects on mental health, pulmonary health, GI health, bone health, muscle function." He wrote, "Exercise may be the single most potent medical intervention ever known." Stanford University's Ewan Ashley is a professor of genomics and cardiovascular medicine. He's chair of the Department of Medicine, and he's part of this research consortium working to understand the miracle intervention that has been staring us in the face all along. Ewan Ashley, thank you so much for talking with us today. As I mentioned, we all know exercise is good for us. So what are the questions that you and your team are trying to tease out?
Well, as you mentioned, William, the exercise is really the most potent medical intervention we've ever known. But what's amazing is that we don't actually understand how it works. I mean, imagine a miracle drug that was saving lives around the world, curing cancer, curing cardiovascular disease, but we never actually worked out how it works. The amazing thing is that exercise has all these effects, as you outlined, on different systems, on different diseases. But to this point, we've really not had the studies and not had the tools available and not had the methods for analyzing large amounts of data to really understand how it works, because exercise has its benefits on skeletal muscle, on the heart muscle, on the lungs, on the brain, on the bone. So where do you even begin to start? And that's what our consortium has been trying to do over the last few years.
How do you explain that lack of knowledge? I mean, if we have known for so many decades that it is so potent, have we just not been asking the questions? How do you explain that?
Yeah, it's an interesting paradox in a way, because exercise is really just, as you said, staring us in the face. And there have been good studies over the years, sometimes population studies, where investigators have looked at individuals over many years, hopefully a very large group of people, and measured certain things about them. But those are the things that you can access. How many steps they take, for example, might be one thing. You can ask them about their activity. You can ask them about their diet. That kind of study has been done. There's also been some studies in labs looking at individual muscles, say, or individual cells. But we haven't really had the technology until just a few years ago to be able to look essentially at every single level of molecule, at the molecular level, to really understand how exercise works. And so the idea of the MotorPack Consortium is to try to build that molecular map of exercise. And it's not cheap, and it's not easy, and it requires a lot of people to come together. So I think that's probably one of the reasons why over the last decades, and it's been 70 years since we really started to understand how potent exercise was, It's taken that time for us to really start to understand how it works.
So the first part of your study worked with rats. I know you're working with humans currently. You exercise the rats, and then you look at how their bodies and organ systems changed. How do you do that? How do you get rats to exercise? Are they willing participants in this?
Yeah, they don't volunteer. They don't sign any consent forms, but they are actually willing volunteers. In fact, rodents love to run. They're nocturnal animals, and there's a few twists around how to do the study because they like to run at night, and humans, of course, mostly operate during the day. So we certainly learned a few things about rodents and exercise during the study. But actually, yes, if you put them on a treadmill, like a bit like a running wheel, we're used to seeing that in cartoons and on TV, or maybe we have pets at home, they actually love to run. And they'll run pretty far and pretty hard. But if there isn't that availability of a treadmill or a running wheel, then they actually are pretty sedentary. So we're able to mimic the situation that we're also studying in humans, where we start with sedentary animals, sedentary humans, and train them for exercise so that we can really look at the tissue level changes that happen over the course of a 12-week training program.
And what were, I know these were the initial results published in Nature a couple years ago. What were the headline results from that rat study?
Yeah, I mean, the thing that surprised me, and I've been studying exercise for 30 years, and I was surprised by some of these findings. And the thing that surprised me was just how different the rats were at the end of training. And this is a pretty short training spell, 12 weeks of endurance training, compared to the beginning. I mean, they were like different beings. They were almost like they changed into different organisms. Every single tissue was different. Every single tissue was changed. And so that, I'd say, was the first really kind of headline finding, was just how different things were. The second was, we understand that exercise kind of stresses our system a bit, but we also understand that it helps with all these different diseases. It helps reduce the risk of all these diseases. So how does a stress manage to reduce the risk of disease? Some part of that we began to tease apart in thinking about sort of training your cellular systems to deal with stress. In this case, a benign stress, exercise, actually helps deal with a disease stress that might come later. So another kind of headline finding was the mechanism around dealing with stress. They sometimes call that hormesis, where you stress a system in order that it can be better trained to deal with other stress. And then I'd say the other big headline finding for us, again, I've been studying this for many years, and it was surprising to me, the difference between the males and the female rats was just remarkable. And this was the case for the sedentary group, and it was also the case with their response to exercise. And so really, after seeing this, I think I've got to the point where I would say every single study from here on in, we absolutely have to study both sexes and think about them in different ways, as well as obviously together.
I know that's been a big, a gaping absence in a lot of scientific research in the past. Can I go back to something you mentioned before, this idea of stress? I think for a lot of people, not in the scientific world, they might hear that and think, wait, are you saying that the stress that I might feel about something about my child or getting a work deadline done is the same as the kind of stress you're putting? Those are different types of stress.
Yeah, I think that's a really important point, because I think we understand well, and I'm a cardiologist, and I see patients with heart disease, of course, and who are at risk of heart attacks. And I spend a lot of my time talking to those patients about work-life stress and how it's bad for the heart. And there's no doubt that's true. That's kind of a chronic level of anxiety, or a chronic level of worry. And we have to do our best within our lives to reduce that kind of stress, because we know that that increases our risk for heart disease. This is a very benign form of stress. In fact, it's really a physical form of stress. And the very fact that it is intermittent, so therefore temporary, is one of the key features. It's not there all the time at sort of a low level in the background. It's actually something that we do literally actively, and then we rest and recover. And the rest and recovery part is an important part of the stress of exercise, and sort of training our body systems, our cellular systems, to deal with the stresses of life that ultimately lead to inflammation, and that ultimately lead to the chronic diseases that we know well: high blood pressure, diabetes, heart attacks, strokes, and cancer.
I see. So you're putting the stresses here are the exercise regimen that the rats were undertaking and that the humans are undertaking. I'm just struck by what you said before, though, that the rats, after such a short period of time, 12 weeks is not that long to be training, seemed like different organisms to you. I mean, do you really think that if you had come in and been presented with these rats, not knowing the intervention you had done, that you would have been able to see with a little bit of an investigation such a demonstrable distinction between then and now?
Yeah, I think it's a great point. One of the advantages of this era we're in, where we can measure so many molecular entities, we call each of them omics, because if we're measuring genes, we call it genomics. If we're measuring proteins, we call it proteomics. And so if it's metabolites, we call it metabolomics. So the whole range of like how many molecular entities can we measure, that science is called omics. So we're currently in a world of multi-omics. And the great thing about that, it obviously causes challenges with analysis, but one of the things it allows us to do is to have computer methods go and look at the data and tell us what are the big signals that you see. So we don't come to it with an idea. For example, we could have come up and said, well, we do think there's going to be a difference between male and females. We certainly did, but we don't have to give the computer that hint. It's so obvious from the data. And one of the advantages, a lot of the time in science, we're looking for really small changes. And we use really finely honed statistics so that we can be very rigorous about when we're seeing a change and when we're not, understanding the variation day to day, for example, or animal to animal. With exercise, there's almost no need for statistics. You look at the data and things are so different that it's just very obvious. It's certainly the biggest signal I've ever seen in my life
Wow.
as a scientist.
Wow.
This is the signal of exercise.
I've heard you mention this before. This wasn't part of your study, but this was a study of 500 million people, an exercise study, and you were saying that a minute of exercise can add a certain amount of benefit to one's life. What is that data again?
Yeah, I like to tell this to my patients who are always telling me they don't have time to exercise, but it turns out that basically you will extend your life if you exercise. And in fact, when we've studied large populations, and groups have studied populations even up to 500,000 people, as you mentioned, then 1 minute of exercise buys you 5 minutes of extra life, which is just remarkable. And in fact, if you do higher intensity exercise, which is safe for most people, you get 7 or 8 minutes of extra life. And so as I like to tell my patients, you definitely have time to exercise because you're going to be extending your life. And I think it's a really interesting way just for people to make it sort of concrete, the idea. Because if you say, well, you should go and exercise, well, that's one thing. But what is it actually going to change? A newer study actually just came out a few weeks ago in the UK biobanks. There's a 500,000 group of people who volunteered to give their data sort of for the public good. And a study of a smaller number, about 60,000 of them, looked at the combination of lifestyle features. So diet, exercise, and sleep, which is really the triumvirate, the three things that you really want to try to optimize in your lifestyle. And it turns out that just a few minutes improvement in sleep, a few minutes of exercise a day, and a little improvement in your diet can add a whole year of life to your life.
Wow.
And if you optimize each one of them, and this was, to me, was the most remarkable thing. Let's say you manage 7 or 8 hours of sleep a day. Let's say you manage 30 to 40 minutes of exercise, could just be walking every day, and that you improve your diet to think about in the direction of mostly fruits and vegetables, then you can add 10 years to your life, 10 years. And most of that is healthy life, because that's the other part. It's like you don't want to live longer if you're riddled with disease. But if those are healthy years, then I think most of us would take a few more.
I mean, these numbers are just kind of jaw-dropping. The idea that these interventions, again, not like you have to go buy expensive gym equipment or try to sleep a little better, try to eat a little bit better, try to exercise a little bit more. It seems so extraordinary. One of the other things that jumped out too is that in the rat studies, at least, that you were seeing all these benefits in systems that were not obvious, at least to my lay eyes, that you'd expect heart, lungs, muscles, ligaments, bones. You'd expect those to benefit from exercise. But you were seeing impacts on all other sort of seemingly unrelated systems.
Yeah, that was a really surprising thing. And I think we just haven't done this before. We just haven't literally sort of looked at every single tissue in the body of an organism that has been subjected to an exercise regimen. And so we were starting to see changes. I mean, good example in the small intestine. So you think about your gut as really shutting down during exercise. We even teach our students, like, when you exercise, your blood gets pushed to the skeletal muscles that need it, to your brain, your eyes widen, and all of these things happen that relate to fight or flight, this sort of literally the adrenaline response, and the rest and relax part, which would be the digestion, your liver and your intestine, would basically be shut down. But over time, your intestine is changing too. And then maybe to the point we just made, that the organ that changed the most was the adrenal gland. The adrenal gland produces adrenaline. So maybe that's less surprising, but it's just not a gland we've spent much time thinking about. Like you said, we think about heart and lungs and the skeletal muscle and maybe brain. But we were seeing very surprising changes. And in the intestine, interestingly, one of the things it does, it's one of the entry points to your body. So it becomes really important as an immune system compartment. So it's part of, in a way, part of our immune system. So across these tissues, including the intestine, we were seeing changes in immune system genes. And I think some of that benefit, if you think about the benefit for chronic diseases that have an inflammatory component, or cancer that definitely has an immune component, then if we're boosting our immune systems with exercise, then that starts to be another mechanism to explain some of that benefit.
Oh, it's so interesting. I know the second part of your study was working with humans as well. Some of that data is starting to come out. And what can you tell us about the results that you've been finding with us bipedal folks?
Yeah, two legs, not four, and a bit less fur. Yeah, that's an important part actually of the thinking about how exercise and exercise capacity has played a role in our evolution. But perhaps we'll come back to that. Of course, the study has been focused on humans from the start. In many ways, the rat study was our stepping stone. Of course, there are things like all the organ changes, as you mentioned, that we can get from the rats that we won't get from the humans. But we did get well over 1,000 humans who were willing to have muscle biopsies, so little pieces of their skeletal muscle taken out and examined, as well as pieces of their fat and blood. So these were individuals who started sedentary and who agreed to come and be randomized into either a group where they would do endurance training or they would do resistance training. And then they would, after each session, not each training session, but at certain points along the way, would have these muscle and tissue, fat tissue biopsies and blood tests. So we're really grateful, first of all, to the individuals who volunteered to do that. These are really special people who really helped us advance science. And it's exciting. Yeah, the first group of data is coming out from that study just around now. In fact, one of the things we do with the study is we release the data to the world so that any scientist anywhere in the world can access it and do their own analyses, because we just think the data is so rich. We really want anyone who's interested in the world to do their own analyses. And so the data is already available online. But yes, we're starting to see some of the human changes. And then, of course, that opens the door to comparing them with the rat changes, to comparing humans with each other, to comparing endurance exercise with resistance exercise, and to look at just how different we as humans are after a period of training with exercise.
So I know people listening to this will be thinking, oh, okay, doctor, enough with the research, cut to the chase. What do I need to do in my own life to maximize the benefits that you are looking at on a molecular basis? So what do you tell people who think, oh, they learn that you're a researcher who studies exercise, and they say to you, what should I do? Does it matter when? Does it matter how much? Does it matter how many days? Does it matter hard, gentle? What advice do you counsel people?
Yeah, well, the most important thing, first of all, is that any amount more than you're currently doing will provide you benefit. And so I think a lot of people do. They hear the research, they understand the data, but they also maybe turn on the TV, and the Olympics are on right now, and they see, elite athletes. And maybe that's a little scary to them, thinking, well, maybe I need to have a gym membership, or maybe I need to go buy some gym gear. And that can be quite intimidating. And so my first piece of advice to all of my patients, and really anyone who asks, is that anything that you're doing, anything that you do more than you do now is worth it. And it can make real changes, including to your lifespan. So if you sit a lot at work, well, stand up. If you can take a standing meeting, do that. If you can take a walking meeting, do that. See if you can fit it into your day, because it's the most important thing is that you do it regularly. When you do it can matter. For some people, they have to, it's a scheduling issue. So if you can get up earlier and do it, that will help a lot. Walking after dinner, for example, is a great time to do exercise, because your body is digesting at that time. And so your insulin resistance, which is the part of the mechanism through which many people eventually get diabetes, is improved if you walk after dinner. So walking is good enough. Standing is better than sitting. But if you want to really optimize your benefits in the way that we've talked about in these trials, then you're talking 30 to 40 minutes of moderate to vigorous activity. I would say try to do that 6 days of the week, because habit is what counts, and doing it regularly is the most important thing.
6 days a week, that's what you tell your patients? People must not like coming to see you as a doctor all that often.
Well, especially when I tell them they have time to exercise, for sure. But there's so many mental health benefits as well to exercise. And although it is using up energy to exercise, most people feel much more energetic after exercise. They also sleep better. And so, yes, I sound like a broken record. People love to come and hear this.
As you well know, the WHO has done these analyses. They argue, as a species globally, we are terrible. I think it's only 1 in 4 of us, I believe, that are getting the appropriate amount of exercise, and their recommendations are much less even than you're suggesting. Do you believe that this research will help people recognize this remarkable intervention and take these little steps? Is that part of your goal here?
It absolutely is. I mean, I think we're having this conversation, and hopefully people are listening and hear just how little they have to do more than they're doing today to get that benefit. I think that at the end of the day, our molecular study can do more. I mean, I very much hope it inspires people. And I often have this idea that maybe we could count up the number of extra steps each study kind of inspires, and you could map that to just how many years of life might be saved. Which I think is an interesting way to think about it. So just having the conversation is one thing. But when we think about unlocking those molecular effects of exercise, people often ask, well, what about an exercise pill? Sometimes they're like, well, maybe I don't need to exercise. Maybe you can develop a pill for me. And while I don't think there will ever be an exercise pill, I think it is possible, very possible, in fact, already happening, that the data that we generate will allow people to understand the health of our organs in a way that will very much help us develop drugs for diseases that we know have a high death toll today. So I think there will hopefully be many benefits, both on a population scale and even on a drug development and a sort of beating disease kind of scale.
And lastly, just in the minute we have, you believe that because of the complexity and the comprehensiveness of what exercise does to the body, that's why we're not going to see a pharmaceutical intervention?
Yeah, I think that's exactly it. I just don't see a way that any one single magic bullet can do all of the things that exercise can do, because it's truly multi-system, every organ, every system. But I think by dissecting it down and doing the science, I think we can find a lot of positive arenas where we can potentially intervene with new drugs.
Well, Euan Ashley, it's so great to talk to you. Here's to your research assistants who agreed to give up a small pound of flesh for your work. I know people can go to the MotorPack website and find more about your reporting and your research. Thank you so much for talking with us. Great to see you.
My pleasure. Thanks for having me.
Before we go, we want to tell you about one of the inquiries that first teased out what we've been talking about here, that physical exercise can yield big benefits. It goes back to post-war London. In the late 1940s, doctors were concerned with high rates of heart disease and heart attacks. Was it the environment? Was it stress? A young Scottish doctor named Jerry Morris suspected it might have something to do with people's work. So he did a large study of the transit workers on the London's famous double-decker buses. There's a driver in that little compartment and a conductor who goes around the bus all day collecting fares. 2 workers, same bus, same hours, same environment, breathing the same air. But when Morris and his colleagues studied over 30,000 medical records of those transit employees, they found a huge disparity. Their study, published in 1953 in The Lancet, found that the conductors had far lower rates of serious heart disease than the drivers, and the drivers died earlier and more often. It seems that going up and down those bus stairs all day conferred a major benefit for the conductors compared to the sedentary drivers. Morris and his colleagues also studied British postal workers and found similar results. Those who walked or biked their delivery routes had lower incidence of heart disease than people who worked in offices as clerks or answering phones. To modern ears, these results sound obvious. But Morris's paper, 73 years ago, was greeted with a good deal of skepticism. We now know it to be a landmark study, one of the first times that scientists began to understand that exercise wasn't just good for us, but it could sometimes mean the difference between life and death. That is it for this episode of Horizons. Thank you so much for joining us. We'll see you next week.
Support for Horizons has been provided by Steve and Marilyn Kerman and the Gordon and Betty Moore Foundation. Additional support is provided by Friends of the NewsHour. This program was made possible by contributions to your PBS station from viewers like you. Thank you.
You're watching PBS.